Then we're going to talk about this method of undetermined coefficients. And this is just a method of basically obvious guessing. So it's sort of like obvious guessing. And there's only one thing that's not obvious about it. Okay, I'll explain that once we get to it. But we can do this basically we can demonstrate this basically by example. So here's the example. 2y double prime plus 3y prime plus y equals t squared plus 3 sine t. So remember the setup, right? We are trying to solve a non-homogeneous system, right? And so the game is first to solve the homogeneous system, and then guess the solution to the non-homogeneous, right? And then you take your obtained solution to the non-homogeneous, and then you add on the space of the solutions to the homogeneous, and that's your solution set. So the only thing that we need to do is to make a guess as to what's the solution of the non-homogeneous, right? And we're going to do that in pieces because we said as long as we solve this thing in pieces, we can add those pieces together, right? So we will first thing to do is to solve 2y double prime plus 3y prime plus y equals t squared. And then next we'll solve the same thing where the g function is 3 sine t, and then we'll add those guys together and get a solution. So this sort of thing is you see something like this, and what's your obvious reaction? What's your immediate reaction? I want something whose second derivative plus the first derivative plus itself is this polynomial, right? Is a quadratic, right? It's t squared. So you think, well, I'm going to take my guess is that y is going to be some sort of a t squared plus b t plus c. Right? It's going to be some quadratic, right? And then you just plug it in and see what a, b, and c need to satisfy, and then you get the answer. The end. Should we do it? Let's just do it. So, right, so y prime then is 2at plus b. Y double prime is 2a. Right? So you plug these things in. Right? So your guess, you make this guess that some quadratic function is going to be the solution. And you say, okay, well then it's going to be that 2y double prime plus 3y prime plus y is going to be t squared, right? And so you get that at squared plus, where are the t's? We get 6a plus bt, and then what are the constant terms? We get 4a plus 3b plus c is equal to t squared. Right? Have we made a mistake? Yes, I have. Right? This is 2 differentiate 2a. Have I made a mistake? Are there a mistake in my notes? Is there any mistake? Let's check. A squared plus b plus a squared plus b plus c. Differentiate, we get 2a plus b double prime 2a. Right? Then plug that in. 2 of 2a. Right? That's 2 of 2a plus 3 of 2at plus b plus at squared plus bt plus c is equal to t squared. Right? And then we look at the t squared terms. That's the t squared term. Where the t terms, this and this. Right? So we get 6at bt, 6a plus b. And then we get 4a plus 3b plus c. Oh, I think that's right. Okay. Okay, so what does that give us? That gives us that A, what does that give us? Well, you know, like you have this guy is the same thing as, this quadratic is the same thing as this guy, right? And so you know, by your knowledge of Taylor polynomials, right, that if you've got two polynomials and they're exactly the same, then the coefficients must be the same, right? So this, you know that A must be 1, that 6A plus B must be 0, that 4A plus 3B plus C must be 0. Because you can't have two Taylor polynomials being identical and having different coefficients. Right? So A is 1, and then, so we get 6 plus B is 0, and so B is minus 6, right? And then we get 4 plus negative 18 plus C is 0, so C is 14. Right? And so that turns out to be the answer of this first one. That y of t, then y of t being t squared minus 6t plus 14 is a solution. Solves this first one. Solution first one. Okay. Okay. So let's keep on going. Is that okay for everybody? I think the only thing that has a little bit of subtlety is this comment about the coefficients. Right? That, well, you know, how do you know that these coefficients are 0? That's actually, you know, you can think about Taylor polynomials. Right? If you've got two polynomials and then they agree, well, then they're forced to have the same coefficients. Brian?
If you wanted to check that y2 is correct, we just plug it back into
Just plug it back in and see if you get t squared. Right? As long as you didn't make any errors, they should be all right. But I made an error in minutes. So. Okay, so that's the first part. And then the second part is just you solve then 2y double prime plus 3y prime plus y is equal to 3 sine t. Okay, and again we solve this by sort of smart guessing. Right? So what are you going to guess as your solution? What's the solution? What's a possible form of the solution?
Some combination of sines and cosines?
Some combination of sines and cosines. Perfect. Right? So you say, well, I'm going to guess that this is going to be a sine t plus b cosine. Right? In that case, y prime is going to be a cosine t minus b sine t. Double prime is going to be minus a sine t minus b cosine t. And you plug this back in, you get 2 minus a sine t minus b cosine t plus 3 y prime, so a cosine t minus b sine t plus y, that's a sine t plus b cosine t equals, you want that to equal 3 sine t. Okay, and again, we look at the coefficients. Well, what coefficients do we have on sine t? We've got minus 2a, we've got minus 3b, and we've got another a. And then for the coefficients of cosine, what do we have? We've got minus 2b, we got plus 3a, excuse me, plus 3a, and plus b. Okay. So we get minus a minus 3b So B is equal to 3A, in particular, B is equal to 3A, and you work that out however you feel like, and you get A is equal to minus 3/10, and B is equal to minus 9/10. Work it out as you would. You could use linear algebra, you could, use substitution, whatever. Substitution is the fastest. Okay, and so, going back to here, a sine t, so we get negative 3 over 10 sine t minus 9/10 cosine t is our solution. Is a solution for this case. Okay, and so together, so putting those together, 1 and 2, gives us that t squared minus 6t plus 14 minus 3/10 sine t plus minus 9/10 cosine t solves the non-homogeneous problem. We've managed to guess a solution. And this is not all that different from just guessing, right? You just look at it and say, this thing is going to involve some quadratic, it's going to involve some trigonometric functions. And then you figure out what it must be. That's why this is not particularly detailed. Okay, and then the only thing left to do is to solve, so last we need to solve the homogeneous problem, right? So we end up with, we look at x squared plus 3/2 x plus a half is 0, right? Right? You do the quadratic equation on that, you see that the roots are minus 1 and minus a half by the quadratic equation. Because the roots are minus 1 and minus a half. And so the solutions to the homogeneous, the fundamental set, fundamental set of solutions is just going to be e to the minus t, e to the minus a half t.
How did we get to that x squared
That's from here, right? Remember, I mean, I've divided everything by 2,
Okay.
but I mean, you could just leave it. You could just leave it here. 2x squared plus 3x plus 1 is the same.
Oh, then we're just solving.
Yeah, we just solved it. Right? Remember, you take e to the RT, you plug it in, and out pops a quadratic times e to the RT. Okay, and so that's the end, right? Right? You get your fundamental set of solutions, and so you know that, so the solution set of n is this guy, right? T squared minus 6t plus 14 minus 3/10 sine t minus 9/10 cosine t plus c1 e to the minus t plus c2 e to the minus a half t, where c1 and c2 range over the real numbers. And that's the total set of solutions.
So,
Yeah.
the
I'm just trying to wrap my head around what exactly all of that means.
All this means is that,
I mean, like, just like, what's the equation, like, the actual solution?
oh, what is the solution?
So, like, it equals 0 at that, basically?
No, it means,
Or no, it equals 3 sine t at that.
so we have just found all solutions to this problem, right? The only functions that satisfy this relation, you plug it into here and out pops t squared plus 3 sine t. They're all going to be of this form. That's the answer. Right?
Is it possible to do like another guess that would be a solution?
Well, you see, ultimately you're going to end up with this, right? So I guess, wait, not, well, okay, so in some sense you have a bit of leeway because you've got trigonometric guys and you've got exponential guys. So it's possible that you could have something different here and it would be subsumed into the constant on this thing, right?
Okay.
But then actually you'd be introducing complex constants here. Because why am I saying this? It sounds fancy, but it's not really big. Right? Even minus t, right? That's cosine t plus I. I'm sorry, cosine minus t. Cosine minus t plus I sine minus t. Right? So it's possible that you could sort of mix this thing up here and compensate for it down here. Right? So yeah, it's possible. But I think you'd be introducing some imaginary numbers. Chris, did you have a question? Okay, straightforward, right? Nothing fancy. This is far from deep. Okay. There's another one along the same lines. I'll show you, I'm going to sketch it, and I'll ask you if you really want to do it. Y whole prime minus 2y prime minus 3y equals now 3t to e2t. So again, the thing is basically what kind of thing are you going to use as your guess? So basically, you have depending on this term, you're going to make some guess, right? And it's basically just obvious guesses to make. And the book basically says, if you have this sort of term, you make this sort of guess. You have this sort of term, you make this sort of guess. So even if you aren't thinking at all, you can just remember those things. Okay. But if you want to think about it, so what should we, what kind of thing, when you differentiate it a couple times, and we'll end up with something like this. Awesome.
I was going to say, I thought I had something else that I'm not really sure.
Okay. Do you want to make a guess? No.
Well, it could, when you differentiate it, it's going to be something like times e to the 2t, but it's going to be on the form like with t to some other power.
The trouble is, if you put a power on the t,
Not in the exponent, but on the outside of the equation. Right?
oh, some other coefficient.
Right.
Yeah, okay. So yes, you think, well, I'm going to have maybe something like at e to the 2t, right? Something like that. Okay. And maybe just to give us a bit of freedom, you throw in a constant. So at plus b, you throw in some, maybe you make this a linear diagram than just a pure. Okay. And indeed, this turns out to be the right guess. So you guess that yt is going to look like this, and then you differentiate a couple times, you get some things, you plug them back in, you get relations between a and b, you figure out what a and b must be, and that's the end. Right. So let me sort of gonna skip over the calculation part, because that part you can all do, like you can all differentiate, you can all substitute back in. Okay, and actually you can do the next one, you can do all of it. Just skip it. No, I'm not gonna skip it all. I'm gonna skip some of it, and then you end up with something like this. You end up with 2a minus 3at minus 3b e to the 2t equals 3b e to the 2t. This is what you end up with, right? And you see what happens, right? Again, you know that this 3 minus 3a is going to have to be equal to 3. You know that this 2a minus 3b is going to be equal to 0. Right? So a is minus 1, b is minus 2/3. Right? And so you end up with your solution, a equal yt being minus t minus 2/3 times equal to 2t is a solution. Yes.
So say you guess, like back up with the guess, just AT,
Yeah,
the 2T.
yeah.
So where would you figure out, because,
You ultimately it wouldn't work out,
okay,
right? Ultimately it wouldn't work
you'd
out.
just get something that was impossible?
Yeah,
Okay, so that's how you know your guess is wrong,
Yeah.
you just cannot find a solution?
yeah.
We're guessing like AT plus B times E to the, whatever T, will that pretty much always solve, or be a solution for
Right,
anything of like
exactly.
something times TE to?
Exactly.
Is there another method to solve these besides guessing? Or is this just the only method to solve these types of problems?
So there's a far cooler method, which we'll get to right after this.
Okay.
But it's going to try to once we get past this, we'll show you something far more interesting called the method of variation of parameters. It's sort of related to D'Alembert's method, where you take advantage of your one known solution. Yeah. Go ahead.
So in this case, are the only solutions to the problem the one we just found and then the fundamental set?
Right, so what we need to do, again, we need to solve, next we need to solve the homogeneous problem, right? And you get, as before, you end up with, now it's e to the 3t c2 e to the minus t. This turns out to be the fundamental set of solutions, and then you take this one guy and add on all combinations here, and you get the solutions to the non-homogeneous guy. There's one thing that could go wrong. So there's sort of like a peculiar case. So there's something that could go wrong, and let me show you what happens. So you have something like this. Okay, you have something like this, and again, you make your guess. Yt is some combination of cosines and sines. Okay, right. Y prime t is 2a minus 2a cosine 2t plus 2b sine. 2b cosine 2t y double prime t is minus 4a cosine 2t plus plug it back in, and you get 4a minus 4a cosine 2t plus 4b minus 4b sine 2t. Okay. And you're hoping that that is going to equal to 3 cosine 2t. So you're looking for a and b for which this is true. Okay, but there's trouble, right? The trouble is that no a and b will make this to be true because you get 0 on the left side. So there's trouble. No a, b works. And the reason is that as we're seeing here, the reason is that cosine 2t, sine 2t are actually solutions of the homogeneous problem. That's basically what we're seeing when we plug this back in. We get 0. Right? Any combination of these guys gives you 0. Right? So these guys are actually, just by our bad luck, the things that we guessed were the solutions actually were the solutions to the homogeneous problem. So it didn't work. Okay. So in that case, you play a trick. You guess that y is a t. You multiply the guys by t cosine 2t plus a t sine 2t. And you keep on going from there. That could also fail. If that fails, then you, I mean, in this case, it's not going to fail, but there could be some case in which it does, in which case, the worst you're going to need to go to is the t squared. But anyway, this is just, and you're basically going to know what's going to happen by solving the homogeneous problem first. Right? Solve the homogeneous problem first, and then you know, oh, I don't want to use these guys as my guess because I'm going to get zeros out. So solve the homogeneous problem first, and then multiply by some power of t. Okay.
Can this happen with problems that are equal to the other example that you just did? Like, what if that problem we had gotten down and there was no solution to the, or the solution we got was the solution to a homogeneous problem?
I think it's still going to happen.
So then, in that situation, would you multiply the e by a polynomial versus a linear function?
Oh, wait a second. Let me think. Let's see. So we solve that.
Like, what I'm asking is adding, or spacing the power of the guess a good way to keep to
Right.
does that work in every situation to help find the solution?
Right. Hold on. So we are going to get. No, it's not going to happen. I guess it's only going to happen in the case of the train vector. Yeah. Thank you. Okay. Brian,
Backtrack, how do you get e to the 3t?
so we have this thing here, right? It's polynomial. It's lambda squared minus 2 lambda minus 3.
Right.
Right? So we get factoring of lambda minus 3 lambda plus 1. Right? So the roots are 3 and minus 1. Right? So we've got e to the 3t and e to the minus 1t.
I'm not sure if I'm seeing so you said at first solve for the homogeneous problem and see if those are solutions. How are those solutions to the homogeneous? I mean, I know that by doing this you're proving that they are because you get 0.
Yes.
But I guess I'm just by doing that method that we were doing before with the gamma or r,
Yeah.
solving for the roots and stuff.
Yeah.
I don't know how you get cosine 2t.
Okay. What do you have here? Right? What's the polynomial associated? We get lambda squared plus 2. Right? And so you need lambda, so you need lambda is one of those cases where you have, like, this is 2i, that is plus or minus 2i, right? And so you're gonna have e to the 2it, right? Which is, cosine 2t plus I sine 2t, right? And what are the real solutions? Right? These guys are the real solutions. Cosine 2t and sine 2t. This is one of those imaginary ones. Okay, enough of that. Let's go on to the more interesting thing. Method of variation of parameters. And this is due to the great Lagrange. Okay. So let me state it first. Normally I'd like to just puzzle our way through it and then state the result at the end. But I'm going to state it first. It seems like people like to see where we're going. So suppose you have a second order linear non-homogeneous problem, and we call it M, and we know that P, Q, and G are all continuous functions in some interval, in some open interval I. I'm going to make the following mysterious claim. If y1, y2 is a fundamental set for H